Not fun.
All right. So 4.2 now. So this is just a continuation of what we just did. It's an abstractification of it. It's just bringing on one more variable. So I'm going to just go over the procedure because it's nothing really new. It's just solving the same type of concept, but now instead of two variables, three variables. Now, there are plenty of different methods to do this. You can use substitution. That is allowed. I will tell you in my own experience that substitution always ends up being very, very confusing because what you're going to have to do is you're going to have to take two of the equations and solve for two of the variables in terms of the other, and then plug those all into one of the equations. It becomes very, very convoluted. You can do it, and it's fine. The reason I bring that up is to tell you that there are other ways to do this. Even the way that I'm teaching, which I'm going to be primarily using elimination, even with my method, there are still other ways to do it. So if you know a different way, or if you find a different way that works better with your personality, be my guest. This is just my method. So what I like to do is I like to label all my equations so that I can organize my work properly. So I'm going to call them E1, E2, and E3. And what's good, but also kind of bad with regards to 3x3 systems is that it's more open-ended. You can decide which variable you want to eliminate. So you want to decide which variable you want to eliminate from the beginning and choose an equation to be your eliminator if you're doing my method. So if you wanted to eliminate x, look at all the coefficients on the x's, 3, 5, and 4. There's nothing really in common. There's no specific equation in there that like is a multiple of the other two. That's a factor of the other two. So eliminating x, you could use any of them, and it would work out. It just would take longer. If you wanted to eliminate y, there is a clear choice of which equation to use as your eliminator. E2, because that has a coefficient of 1. That means that you don't need to multiply the other two by anything to eliminate y. So if you're eliminating eliminating y, use E2. If you're eliminating z, on the other hand, then E1 would be the choice because E1 has a coefficient of 1 on its z term, making it quite quick to deal with. So which one do we want to do? Do we want to eliminate y or do we want to eliminate z? Y. That is a good point. I think y is a little easier to work with. And that's because if you look at E1 and E3, the signs on their y terms are both negative, whereas E2 has a positive y. So I don't need to multiply by any negatives if I do that. With z instead, I like one of them is negative and that'll be quick, but one of them is positive, so it won't be as quick. But it's really not that big of a difference. But Alita was the first one to suggest it, so we will be eliminating y. Because y is easier. It's a little easier.
Honestly, I chose it because they both have one.
Ah, the coefficient as well on the other side. Yeah, fair enough. So E2 is our eliminator. We're going to use that on E1 and E3. So we'll do E1 and E2. Start this on the left because we're going to need both sides of it. We're going to kind of split it down the middle. So E1 and E2, let's stack them on top of each other. E1 is 3x minus 2y plus z is equal to 2. And E2, our eliminator, is 5x plus y minus 2z is equal to 1. We want to eliminate y. That's what we decided on at the very beginning. So the first equation already has up negative 2y, so all I need to do is multiply the bottom equation by positive 2. That gives me 3x minus 2y plus z equals 2. I didn't do anything to the first equation. The second equation is now 10x plus 2y minus 4z is equal to 2. And I will add those two things together. That'll cancel out the y's in the middle there. 3x plus 10x, that's 13x. Z plus negative 4z is minus 3z. And 2 plus 2 is 4. And so we notice that when we eliminate one of the variables with one of the equations, we get a two-variable equation now that we've reduced it. And if we do it again with E2 and E3, we're always using our eliminator, E2 and E3. So E2 is 5x plus y minus 2z equals 1, and 4x minus 3y plus 3z is equal to 7. Slow down and let you write that out because that's quick. This time, we're still removing y. We're still eliminating y. So we need to multiply the top equation by positive 3 so that they have the same number but opposite signs. Well, this one by 3, which will lead us to 15x plus 3y minus 6z is equal to 3. Squeeze it in there if you can. And then 4x minus 3y plus 3z is equal to 7. And we will add those two things together. You get 19x minus 3z is equal to 10. So in doing this, we've reduced our 3x3 system to a 2x2 system, which very scientifically is called a baby 2x2 system. That's what they call it in all the textbooks. Trust me. No, they don't call it that. So now we'll solve that system by any means necessary. So we have 13x minus 3z equals 4, and 19x minus 3z is equal to 10. I would not recommend using substitution, but you could if you wanted to. And I would recommend elimination, and I would recommend eliminating z because they already have the same number. They just need to have opposite signs. So we can either multiply the top one by -1 or the bottom one. It doesn't matter. I'll go ahead and multiply the top one by -1, but that is purely by convention to do the top one. There's no reason why I couldn't have done it with the bottom one instead. That gives me negative 13x plus 3z equals -4, and 19x minus 3z equals 10. And we'll add those two together. The z's cancel. We get 6x equals 6, which gives us x equals 1. Then we can use either one of the original equations in the baby system to solve for z. So I'll just use the bottom one. 19 times 1 minus 3z is equal to 10. That's negative 3z equals -9, and z equals 3. Okay? So we've solved the baby system. We found we found two of the variables. Now that we have two of them, we can replace those two in any one of the original three equations. I suggest use the eliminator, but it doesn't really matter. Though any option will work. Though any option will work. I'm just doing the eliminator so it's kind of clear in the like just for consistency, but it's not required. So the eliminator was 5x plus y minus 2z. So we have x equals 1, z equals 3. And we'll use our eliminator, which was 5x plus y minus 2z is equal to 1. Using this information, we've got 5 times 1 plus y minus 2 times 3 for z equals 1. That's going to be y minus 1 is equal to 1. That gives us y is equal to 2 because it's going to be 5 minus 6. That's minus 1. Add the 1 to the other side, you get y equals 2. So, and we'll underline that so we have it all in front of us. Our answer to this one, because it's in 3 space, it's got 3 variables, will be an ordered triple. It'll be an x comma y comma z. So that's going to be as easy as 1, 2, 3. Ha! I did that that's totally by accident.
Well, this is fine, does this mean it's like 3-dimensional?
So this is a 3-dimensional situation. So in 2 space, a linear equation is a line, but in 3 space, it's something different. And then, of course, step 5 is optional, but you should check your work. Check it in either one of the equations. If it works in 2, call it good. You don't need to check all 3. Couple things about this. So, as you've seen on both this and on the 2x2 systems, there's a lot of arithmetic and algebra going on, right? There's plenty of chances for you to accidentally make a mistake. I almost made a mistake and forgot to multiply the 4 by -1 in this case. And that would throw everything off. And so what I can tell you is that on your homeworks and on the exam, they usually like to choose either nice numbers or nice fractions. So what I mean by nice fractions is things like 1/2 or 3/4 or -1/5. If you start getting 17/99 or 8/62 or something like that, that's a good indication that you probably made an algebra error somewhere. So if you start getting some nasty fractions, take a step back and retry the problem. And then as a reminder about retrying problems, try it on a new paper. Don't look at any of your old work. That is a surefire way to go in the same, keep hitting the same wall, because you'll look at your work and think it's correct, but it's not. So if you need to retry any problem, always try it on new scratch paper. I have plenty with me. There's always a page of scratch paper at the end of our exams, but I will provide that always every time, okay? So if you aren't getting nice numbers or nice fractions, probably an indication that you need to try, you need to mess around with it and try again, okay? So now, to Ben's point, a 3x3 system has an ordered triple. That is the solution to all of them. There are 3 variables and 3 equations. So a solution is a point in 3 space. It's 3-dimensional. And so, in fact, every linear equation in 3 variables represents a plane or a sheet. Most people call it a plane, not like an airplane, but a plane. It's just a flat piece of paper. So the cool thing about linear systems, the reason why it's called linear algebra is linear algebra, almost all of it is studying linear systems, because linear systems are much nicer than nonlinear systems. Linear systems either break down into one of 3 categories. Either you have inconsistent, so there's no solution, consistent independent, where there's infinitely many, or you get one unique solution. With nonlinear systems, you can have 10 solutions, 15 solutions, 80 billion solutions. It all depends. And so this is what they all look like. And it took a long time to draw these. I made these. We are using what's it called? using this program, actually using Notability. If you wanted to do inconsistent, there's three different ways that could happen. Either all three planes could be stacked on top of each other, but never touching. You could have them intersecting the red one, but not actually intersecting themselves. So the red and the green have points in common. The red and the blue have points in common, but they don't all three have points in common. Or you can have them all intersecting each other, but never all at the same spot. Those are all the different ways that you could be inconsistent. And then you could have consistent independent, where you have one unique solution right there, where all three of them, and I've drawn them all perpendicular, or what we call orthogonal in upper division math courses, because once you add an extra dimension, perpendicular doesn't make as much sense because there's two different types of parallel or perpendicular. You could be perpendicular sideways or vertically, so you call it orthogonal, but it doesn't necessarily have to be that way. It could be slanted, but either way. And then consistent dependent, that's the situation where you have infinitely many solutions. It could be that all of them are all intersecting in a line, and that's the solution. Or it could be that all of them are the exact same plane, so that every point on this plane is a solution. Any questions on that? I bring it up not because it's useful for our exam or anything like that, but it's a good way to visualize what's going on. And one of the things that we do a lot in mathematics is look at lower dimensional things to interpret things about higher dimensions. So this can actually bring us to ask questions to four-dimensional systems. So 4D space, four-dimensional systems, and what the consistent versus inconsistent would look like with a hyperplane is what we call it. Is when you're in 4 dimensions, you call it a hyperplane. Just like a 4-dimensional cube is called a hypercube, and a 4-dimensional sphere is called a hypersphere. Some people call it the 4-dimensional the hypercube. They call it a tesseract, but this ain't the Avengers. We're not interested in that. But either way, so just a fun little visualization. I had fun drawing that. That's the main reason why that's here. So we'll do one well, no, wait, we got out at 12:20, right?
Yeah.
Okay, so we'll come back next time and we'll do these ones. I'm gonna pass back the exams real quick. And sorry, they're not stapled. Something about it. So I just handed them back. As per usual, make sure that everything lines up and is added correctly. I am human. I can make mistakes. I don't make them very often. I don't think I've made an error in the adding up of anything in 8 years. But regardless, I can still make mistakes. There's always a chance for it. So please make sure that all works out properly. If you think anything was graded unfairly, please let me know, and I will either correct my mistake or explain what was going wrong. Additionally, so as you the average was better than the last exam, which was what I was hoping for. The other exam was pretty rough. But if you are looking at that, you might notice on question 2B on page 3, there were 2 options. As per usual, I'm willing to give some extra credit if you do the secondary option as well. How much we want? 1 point. 1 point. 1 point, right? Eric, you want 1 point? 5 points?
That's a 3 on 4.
6.
Darren, do you want 1 point or 5 points?
5 points.
What? 5? Let's call it 5. Call it 5. 5 points extra credit if you do that problem, okay?
And of course.
Oh, please turn these in by Thursday this time. I have to get them into so you've already done you've already looked at several of the problems, hopefully over the weekend. What's up?
Thank you.
So please turn them in Thursday, Friday at the like Friday morning if you need an extra night. I will accept it, but it needs to be sent. It needs to be delivered under my door so I can actually grade it on time.
And of course, you can still do the other problem.
Yes, and get the corrections for it. Yes, absolutely. Any questions about it? Okay, so Thursday, and then if so that way, then I can post if everyone turns it in on Thursday, then I can post the exam solutions for everyone to look at before the final exam. Otherwise, I'll see you guys on Thursday. If you guys have any questions, feel free to talk to me. Otherwise, see you then.